Hello Calculus fans, this video is going to be about how to integrate Secant. This is kind of a case study. This is not essential to my course, but I thought kind of some interesting things popped up. Some students were asking me about this, and I thought about how I would integrate it. And then that got me looking up a few things. So I thought before I showed you how I would integrate this, I would just mention a couple things I'm going to pull up here. So first I did a little bit of research. There are multiple ways to write the answer. This is just the Wikipedia article. But what I found interesting, and I didn't know some of this, is that there's kind of an interesting history. So this problem is stated as one of, an outstanding open problem of the mid-17th century. And that it was solved in 1668 by James Gregory, who was a scientist. I've heard of him before, did a few different things, but they said this integral came up when they were trying to study things about maps or something, nautical tables, which maybe makes sense. You'd be dealing with some sort of angle or something, and they said they approximated it with Riemann sums, but they wanted to know what the actual value was, if they could find a closed form answer. So I don't know if that's interesting. At some point somebody kind of conjectured they knew what it was. Isaac Newton was aware of the conjecture, which means Isaac Newton hadn't solved it. So if you have struggled with integrating secant, then you're in good company, is the point of that. So there are many proofs. It fits nicely into one of our techniques. It appears the first proofs you've used clever identities, which is often how this goes, and then there were shorter proofs. Anyways, I didn't know there was such a history of this. I was always unsatisfied with our textbook approach. A lot of textbooks use this identity, which I find kind of hilarious. Who would think to multiply by secant x plus tangent x over secant x plus tangent x and then use this unusual substitution? That feels like someone who already knows the answer and is working backwards. So I always found that unsatisfactory. I'm not the first one to think of this, but at some point when I was doing, and I don't even know if I might have heard this from someone, so I'm not going to take any sort of credit that I discovered this independently. Again, it's already been around for a long time. But we have a technique for what to do when you have an odd power of cosine. And so it's very natural to just try to use that technique. And the technique we learned for an odd power of cosine, I don't know how, let's do it like this. Let's work across the top. Is to pull out a cosine. A natural confusion with that is that you can't pull out a cosine because there is no cosine up here. But what we're going to do is just rewrite it. So we're going to rewrite this as cosine squared. So that fits nicely. So for those of you that have taken calculus, and with the technique we use for odd cosines is always to pull out a cosine and then try to turn everything else into a sine. So that's fairly standard. And the way we turn everything else into a sine is we write cosine squared is 1 minus sine squared. You might say, well, aren't you using an identity? Yes, I am, but that's the most important identity of them all. But the point of that is now substitution works. So that's kind of a nice recap of, if you're in my calculus class, of the 7-2 methods, which was, what do we do when there's an odd cosine? So that's just kind of a mention of, and I allow students to quote this result in my course, and I mentioned the proof in the book, and I mentioned that I would show you how to do this, but at the time we don't have the techniques. So anyways, at this point I'm going to do u equals sine of x, and that means du is cosine of x dx. So we also get a little review here. This is going to be u squared. And then we have a fresh new problem, which is what substitution does for us. So let's write down the new problem. The new problem is 1 over 1 minus u squared du. In section 7.4, we learn a very systematic technique that doesn't require any ingenuity, which is to do some, so we're going to kind of take a little break and say, factor the denominator. And we call this distinct linear terms. So what I like about this technique is there's nothing here that's really that. I mean, this one observation at the beginning, which is to use the method we already use, and the fact that that makes that a cosine squared. That's the one observation. And you don't have to be clever. I'm not as into clever proofs as over the years I've, I think that people can do these things, and if we always use a clever method, it makes it look like you have to be clever. You just have to pound away. Perseverance here. So anyways, we cleared the denominator, so now I'm reviewing 7-4. We're going to find A and B. There are many ways to do that. I mentioned I might make a separate video about how to very quickly do that. The favorite method, this isn't the fastest method, but the favorite method of calculus 2 students is usually to do this. If you plug in a 1 for u, then you get A times 0 equals implies. So you get 1 is equal to B times 2, so B is a half. Success, and if you put in a -1, you get 1 is equal to A times 2, so A is a half. And then the method is done. We write a half, 1 plus u, plus a half, 1 minus u. That's really it. At this point, we're essentially done with the integral, so I'm going to write 1/2. In fact, let's factor out the half, and then we're going to write log. There is one place that's very easy to make a mistake, which is right here. In general, when you're integrating a fraction like this and the bottom is linear, and maybe I'll come over here and say a few things about a common error. Here we go. So if you have 1 over, let's say, 2x plus 7, it's a linear function on the bottom, so the answer is log. But if you just do this, it's wrong. Because if you take the derivative and do the chain rule, there's going to be an extra 2, and so it turns out you need a 1/2. So it's always 1 over this is. And in this case, the number in front of the variable is -1. So in front of there should be a 1 over -1. So that's very easy to miss. So anyways, so let's wrap this one up. We're almost done. It's a fairly short, but I was explaining and giving some background. So when we're all said and done, we get 1/2 the log. Let me zoom out a little bigger. Sorry if you couldn't see that for a second, if my head got in the way. Get new to making these videos. 1 minus u plus c. And we said u was sine of x. So here's our answer. The integral of secant of x dx is equal to 1/2 the log of 1 plus sine of x over 1 minus sine of x. So we did it. So that was an unsolved integral back in the 1600s. We just did it. Yay. At the time, they didn't have these methods as formalized. And so for us, we have a way to attack. If we sort of follow the techniques using a bit of 7.2 and a bit of 7.4, it's fairly tame. Now, there's a second question, which that doesn't look anything like what modern textbooks typically write it as. When I was doing this earlier, the other day, kind of remembering how I do this, I was like, why is that equivalent? And I had to think kind of hard for a bit about how to get there. So the typical way you see this written is the log of secant of x plus tangent of x plus c. And I was like, what in the world? How am I going to convince myself that that is the same as this? And that's going to take a little bit of work. So I'm going to do one last thing to show you that, which might be of interest in and of itself. So the main maneuver, I kind of saw where this is going. It's going to involve some log rules. So I had some ideas. But when I first saw this, I was like, why in the world can I simplify this? My first thought was to try in some way to turn this into something we can handle. And the first thought I had was, what about the difference of squares? And this is, if you've done rationalizing before, this is a first thought you would have. And I'm trying not to look at my notes because I remember I had to think kind of hard at this, and I'm trying to do all this without notes so you can sort of feel what I was doing when I was thinking about this problem. So what's going to happen? So in the denominator, so this is just rewriting. Right now I'm playing around with this inside piece. Maybe I should look at my notes. But in the numerator, I'm going to have 1 plus sign. And I'm not going to expand it yet. Okay, that's the thing. I was about to expand, and I think that's not the way to go. But the denominator becomes 1 minus sine squared. And that's the engine that makes this go. Why does that make that go? Because that's, we already used it once here. That's cosine squared. So how is that helpful? And now you might be able to see it. Log, it's so tempting to expand out. I feel like I almost did it again. But this is 1 plus sine of x, quantity squared. And the bottom is cosine squared. Now you might want to dust off those log rules. The most important log rule, if you only were going to remember one log rule, it would be this one. This is the log rule we use whenever we're solving an equation that involves some exponential function. So we can use that. In this case, I'm going to have a 1/2 here to move this inside. But if you take all that to the half power, it's like taking the square root. So now ask yourself, what is the log of the square root? In fact, we can even rewrite this fraction as 1 plus sine of x over cosine of x squared. And somebody must have at some point realized this after they'd been working with this and were like, oh, it's kind of a pain to write. So somebody thought to do this. Okay, so then we have the log of 1 plus sine over cosine. And then we're like, well, we can do one better. We can separate these 1 over cosine. And the truth is, none of these answers is better than the other. They're just trying to get the most compact answer so they can easily type it in their book. This is secant. This is tangent. And that's the modern way this is written. So it's the log of secant plus tangent plus c. The real point of that is a lot of these integrals, they don't come out of nowhere. They come out of some significant application of the past. Suddenly they became important. Maybe for a while they were unsolved. And then the techniques kind of built up enough that we had an approach. And there's more than one approach. All right, hope that's sort of interest. Again, for my students, that's just something we can quote. But really, you can see it fits nicely into the 7-2 methods and some partial fractions. All right, I hope that was sort of interesting. I plan to kind of add on to this a few other interesting integrals with some history. All right.